Hello, I'm Rorik Henrikson from Chatham Labs, and I'm here to talk to you today about the paper Head-Coupled Kinematic Template Matching, a prediction model for ray pointing in VR. Up until recently, most of our computer experiences have been in 2D. Logically, this has resulted in a significant amount of research in 2D, and particularly desktop interactions. A subset of this work focuses on predictive interactions and pointing. In recent years, there has been an increased interest in virtual and augmented reality, both 3D systems that often use 6 degree of freedom controllers as ray pointers. However, there has been very little work on predictive interactions in this 3D space. This work focuses on a novel end ray prediction model that we refer to as a head-coupled kinematic template matching model, or HCKTM for short. This work builds upon the previous work by Pascal and Wilbrock that introduced the 2D kinematic template matching model, or KTM. In this work, we augment the initial model by adapting the 2D technique to a 3D environment by considering both 3D position and 3D angle, included head movement into the model, and examined the top-end matching templates. What we found through our studies was that these improvements increased the prediction accuracy of a selection by almost 2 times when only 40% of the way through the trial compared to a direct extension of the original KTM model. So what did we actually do? To start off, I'm going to review the basic premise of the original KTM model to help explain the changes. In short, the model uses a series of velocity templates that were previously captured for a user. When a user starts a new movement, the system takes the velocity of this new motion and compares it to existing templates. It compares the movements by accumulating the difference in velocities for each data point between the curves. This creates a score for each template, with lower scores being better, which are then sorted to select the best match. The distance traveled from the top matching template is then applied to the starting point of this new action in the direction of movement. This process is repeated for each motion frame. To adapt this to 3D, there are obviously some differences. First, rather than dealing with only x and y coordinates in 2D, we have to worry about the x, y, and z position of the controller and target, as well as the controller's pitch, yaw, and roll being a 6 degree of freedom device. As a result, some major differences to keep in mind are that targets can be at different depths, the controller could be starting and ending at different depths, and the user could be pointing at the same target from different positions with different controller angles. However, there is a major difference that we can take advantage of. In 3D, most systems also track the head position and angle. This gives us extra information we can use to help us understand what is currently happening. To account for some of these differences, we made 3 major changes to the original KTM approach. First, instead of trying to predict an endpoint, we rather looked at predicting a ray's landing position, or the position and angle of the controller at the end of the movement. Second, we didn't just look at one velocity curve, we introduced information from the head, which allowed us to consider 4 velocities for each trial: the controller position, the controller angle, the head position, and the head angle. These values were weighted so that we could tune the parameters and combine them into a single score for sorting. Finally, we didn't just consider the top matching trial, we extended the model to consider the top end trials for a movement. More specifically, this is all expressed by calculating the score using the original KTM scoring algorithm applied to all 4 velocities, the controller position and angle, and the head position and angle. We applied a tuning parameter to each velocity and summed them together to get our final score. Finally, the top-end templates are used by taking the weighted average angular distance and applying this to the original angle along the current angle of motion. The same is done for the expected controller location. In this formula, n is the number of trials we are evaluating, w is the weight, which is the reciprocal of the score, and d is the template's angular or movement distance. We conducted 2 studies for this project. I will first outline the similarities between the 2 studies, then talk about the details and results from both in turn. Both experiments consisted of a reciprocal 3-dimensional pointing task in a VR environment using a ray pointer, where participants pointed back and forth in succession between a start and end target with no distractors. The setup can be seen here in the clip being shown. It is worth noting that predictions were not shown to the user during either experiment. For these experiments, we altered several variables: the position of the targets, the depth of the start and end target, the angle between the targets, which we refer to as theta, and the angular width of the targets. We used the angular width of the target rather than the radius, so that the movement accuracy needed for selecting the target stayed the same regardless of how far away the target appeared for the user. With the first study, the purpose of the experiment was to better understand human head and hand behavior during ray pointer movements with controlled target distances and sizes. Since we did not know if we'd be able to infer depth from the results, we controlled the depth of the start and end target to 3 meters, 6 meters, and 9 meters. We wanted to see if the angle between the targets was discernible, so we only used 3 discrete angles between the targets of 25, 50, and 75 degrees. We wanted to compare small targets versus large targets, so used an angular width of 4.5 degrees and 9 degrees. And finally, we placed the position of the target around a circle at 45-degree increments in opposing pairs. For our study, we ran 54 blocks of trials consisting of all possible combinations of start depth, end depth, theta, and angular width in random order. For each block, 4 sets of reciprocal trials were performed, changing the position, and required 8 selections between the 2 targets. This resulted in 1,728 trials per participant. We ran 17 participants, 11 female, through the experiment, recording the timestamp along with the state of the selection button, the position and rotation of the controller, and the position and rotation of the headset at 90 Hz. We later used these recordings to create user-specific trials and templates for our analysis. We saw many interesting results, but I'll focus on a few key results today. Movement time was one aspect we examined, which we considered to be the duration between the selection of the starting target and the next subsequent selection, regardless of if it was successful or not. Analysis showed that the main effects were found with angular width of the target and theta, the angle between the targets. The depth of the target showed no significant effect on movement time. One interesting point to note is that across the 6 combinations of theta and width, the performance trend followed an angular derivation of Fitt's law with an extremely high fit. We also looked at the head and controller angular movements. With these movements, as would be expected, we saw that theta had a significant impact on the cumulative angular distance traveled by the controller and the headset. The target width and position also had a significant effect on how much both the head and controller turned during the movement. It was interesting to see that the head moved further for smaller targets, likely to better see them. This suggests that the head movement may provide information that the controller does not. Depth did not have a significant effect on the angular movement of either the headset or controller, but we did see the head only moved a fraction of the angle that the controller moved. This makes sense as the ray from the controller needs to be on the target when selecting it, where the head only needs to turn far enough for the target to be in the user's field of view. This is nicely displayed in these scatter plots, which show where the controller was pointed in blue and where the head was pointed in orange in relationship to the target when the target was selected. We also looked at how representative velocity profiles compared to one another with different movement angles. When comparing these profiles, the controller velocities were not distinguishable from one another during the initial stage of movement across the 3 movement angles. However, the velocity profiles for the head diverged immediately. This suggests that using head movements with a predictive model may allow predictions to be made within the first 300 milliseconds of a movement. Turning our attention to the predictive model, to determine the model parameters, we needed a consistent metric to compare the results of the trials. To do this, we used the angular accuracy of the prediction, that is the angle between the predicted ray and the perfect ray, the one that goes from the controller through the center of the target. This allowed us to compare the accuracy of the model, much the way pixels are often used in a 2D system. Our model had 2 main factors to manipulate: the best weights for the velocity curves in our scoring algorithm, and the number of templates to use for the top n. Through empirical means, we determined that an n of 7 gave us the best results, and our weighting parameters were tuned for optimizing early prediction 40% of the way through a movement. The controller by itself, however, becomes a better predictor about 55% of the way through the motion. For this study, we saw accuracies on average of 6.4 degrees, 50% of the way through a task, and up to 2.3 degrees at 90%. These are actually very good results when remembering that our targets had an angular width of 4.5 and 9 degrees. So after the first study, we ran a second study. The purpose of this one was to further validate the model and compare it to varying approaches. A major difference between this experiment and the last was that the first one only examined 3 different movement angles, whereas the second experiment evaluated the robustness of the model against a continuous range of angles, depths, positions, and widths. And finally, we kept the parameter values for the model that were set in the first experiment to test them and avoid potential overfitting. Unlike the first experiment, the only controlled variable in this experiment was the angle between the 2 targets, or theta, in which we tested all angles between 15 and 85 degrees at 1 degree increments. The rest of the variables were randomly distributed between the values we used in the first experiment, as shown on the slide here. For this experiment, we broke the session into 50 sections, each with 7 pairs of targets covering all angles in random order, and the users were required to perform 6 reciprocal selections. This works out to 2,100 trials per participant. From the original pool of 17 participants, a total of 12 participants, 3 male, completed experiment 2. This gave us the option to examine behavior across the 2 studies. For the second study, if you'll recall, our model made several changes to the original KTM model. We included the head, and we examined the top 7 matching trials. We therefore refer to it as the HCKTM7, or Head-Coupled Kinematic Template Matching model using the top 7 matching templates. To validate our results for the second study, we compared them to a direct adaptation of the KTM model, a variation of KTM where we used the top 7 results, and a head-coupled model but only using the top matching template. We also took a baseline where we looked at the angular distance from the user's actual ray. The results are shown in this graph. We can see all predictions outperform the baseline, with the HCKTM7 model making the best prediction for the first half of the movement. These results were encouraging as it suggests our improvements do in fact help our predictions. The HCKTM7 also managed to improve accuracy by a factor of 2.7 times, only 40% of the way through the movement compared to the baseline, and a factor of 1.8 times compared to the original KTM model. It is also interesting to note that the HCKTM1 outperformed the KTM7 model, suggesting that the improvement comes more from the head coupling rather than using the top-end matches. For a full comparison of the different techniques, please refer to the paper. The results that we saw with these adaptations were promising. However, there are of course some limitations to the work that we've done. One aspect of 3D VR pointing that was not addressed is that multiple targets can be located along the same predictive path at varying depths requiring disambiguation. Since we only predict the landing ray, the position and angle, the current model does not differentiate between these targets. Similarly, our study did not employ distractor targets, which were omitted to simplify the task environment and capture raw target acquisition movements. Looking to the future, of course the HCKTM7 model is only one possible approach. Comparing our results to similar efforts such as regression-based extrapolation and target classification could yield interesting results. Future models could include probability distributions across possible targets to influence predictions. As well, there are many categories of facilitation one could implement. One could augment the pointer itself, for example by bending or expanding its size, augment the target to help the user, such as using different target arrangements, adjusting the ratio of the controller's perceived movement, or highlighting targets in a different manner. Through all this, one must remember that any facilitation technique will likely change the user's behavior due to the perception-action loop in target acquisition. This in turn may impact the model's performance. A key insight of this work was that it is beneficial to leverage the movement of the head while pointing, as it provides extra information that can be used to help predict a user's movements. This work has also demonstrated that by using an adaptive kinematic template matching model, by including head movement and taking the top 7 closest velocities, ray pointer landing positions can be predicted early in a user's movement. Finally, this work has provided a first exploration into pointer prediction in VR, hopefully opening the door for future enhancements to 3D user experiences. Thank you for listening, and finally I'd like to thank my co-authors, Tovi, Sean, Daniel, and Benko.